Thank you. So, good afternoon, everyone, and I would like to first thank the organizer for this very new, nice edition of EUCARPIA. And I would like also to mention that this work that I will present today is mostly the work of Anaïk Debache. So let's start by just considering one simple example of the topic of the talk. Let's assume that we want to investigate the resistance of a given species, so let's say tomato, to some viruses. So here we have 3 viruses, V1, V2, and V3. So if we want to do that, what we need to do is basically to collect a sample of tomato accession, then to run an experiment for each virus where we will inoculate the virus to each panel. And then after a few days, we will see how the different plants react, and we will collect phenotypes. So once we have the phenotypes, we also have, I assume, the genotypes. We can perform GWAS analysis for each of the 3 viruses, and then we get this nice Manhattan plot that we have here. So what you can observe here is a different landscape of resistance for the different viruses. But what you can also observe is that on chromosome 5, there is a peak that seems to be at the same place for the 3 different viruses. So this raises the following question: are there chromosomal regions that are associated with resistance against multiple viruses? So if we want to answer this question, first we have to make clear what exactly is the hypothesis that we want to test. So here, if we want to look for markers that are associated with at least 2 traits, it means that the H0 hypothesis is that the marker is associated with at most 1 trait, right? So how do we do that? Well, in practice, if you just look at what is done in the bibliography, there is a naive approach that is just to cross the list of candidate QTL. So you have one list of QTL candidates for each of the GWAS. You cross the list, and if you have candidates that appear in several lists, then you have your guys that are associated with more than 2 traits. So why is it bad to do that? Well, it is bad because basically when you do that, you have no idea about what is the type 1 error rate that is associated with your final crossed list. The second problem is that actually you don't know if you are doing something that's smart, meaning that you have no idea of the detection power that you get with this kind of crossing. So what we want is actually to develop a grounding testing procedure for the hypothesis that we have here. Okay, so what is the next step if we want to, the first step if we want to do that? The first step is actually to list all the possible configuration of effects that a marker can have on the different traits. So here I had 3 viruses, so basically we have 3 traits. For each marker, you can have either an effect on the trait or not, so you have 2 possibilities. So 2 possibilities for each of the 3 traits mean 8 possible configurations that are listed in this table. Now, if you have more traits, if you have, let's say, k traits, then you will have 2 to the power k possible configuration of having effect or not on the different traits. So we want to detect markers that have nominal effects on at least 2 traits. So if you scan the list of configuration, you can see that, for instance, marker A is perfectly eligible because it has effect on all of the 3 traits, right? But if you look at marker E, you can see that this one is not an eligible marker because it has only 1 effect on trait 2. So by just scanning the list, you can split the list into 2 subsets. The subset, the first subset that I will call C0 that corresponds to the null configuration, so the configuration we are not interested in because we don't have enough effects, and the C1 subset that gather all the alternative configurations, the one we are interested in, right? Okay, and so you can see that actually splitting the configuration list into these 2 subsets, C0 and C1, give you exactly the composite hypothesis that you want to test. So now I can reformulate what I was saying before. H0 can now be expressed as we want to test for the marker if its unknown configuration C belongs to the set C0 or not. Okay, so the next question is, what kind of data are we going to use to try to answer this question? So I will assume here that we do not have access to the initial data, so we don't have access to the genotypes, the phenotypes. The only things that we have access to are the p-values that were obtained for each GWAS analysis on the different traits, right? So basically, we have only access to this kind of table here. And we will not actually use directly these p-values, but some kind of transform p-value that are called the z-scores. So to get the z-scores, what you just do is that you take the initial p-values and you transform them using inverse normal distribution function. And so why do we do that? First, because p-values live in 0, 1, and z-scores live in R, so it is just more handy. And second, if you look at this toy example, so here you have a distribution of two kinds of p-values associated with H0 and p-values associated with H1. And what you can see is that when you do the transformation, so the Gaussian inverse transformation, basically the H0 p-values are transformed into a z-score that is normally distributed, which is very easy to manipulate. And if you look at the H1 p-values, they are transformed into some z-score that we don't know the distribution, but basically you can see that they have a corresponding high z-score. This is the only thing that we can say. Okay, so assume in the general setting that we have k traits. Define Zm, that is the vector of all the z-scores that you collected for a given marker on each of the different traits. This vector is actually so a vector that has a multivariate distribution that is unknown and that will depend on the configuration C of marker effect that correspond to the marker. So if you know C, you cannot phi C, the unknown distribution of Zm given the configuration, right? Similarly, I can denote WC, the unknown proportion of markers that live with configuration C. And then what I can assume now is that Zm follows what we call a mixture of distribution, where the mixture is given here and depends on the proportion and the conditional distribution. Okay, so if we want actually to perform some kind of composite hypothesis testing, what we have to do basically is first to estimate all the unknown quantities, so the proportion and the distribution, the conditional distribution. Then once we have this, we can compute the posterior probabilities for a given marker to belong to a given configuration C. Okay, so we have here the formula that allows us to do that. And once that we have this posterior probability, you have to remind that actually some of the configuration are of interest for us, some not. So what you will do, you will just sum the posterior probability of all the configurations that correspond to C1. If you do that, you will get something that is the posterior probability of marker M to belong to C1, so to be under H1 basically. And so once you have this, you can get the associated p-value and you have your test. Okay, so this is very easy, basically, except that you have one problem here, which is that you need to estimate all the multivariate distribution, and there are plenty of them. So the question is, how can we do that? And the only answer that we have is that we have to make some strong assumption about these distributions. So I need my slides. Up. Okay, thanks. So the first assumption that we can do is just that this multivariate distribution is a product of univariate distribution. Okay, so we have k different traits, so we have k distribution, but we have two possible states for the marker in a given trait. It can be under H0 or under H1, so it means that we have two k univariate distribution to estimate. So 2k univariate distribution rather than 2 to the power k multivariate distribution, of course, it is much more easy to do. Now, if we do that, basically what we are doing is that we are assuming some kind of independence between the series of p-values. And this is a problem because if you take my example about the tomato, you will see that we use the same exact panel to make the 3 different analyses. So this may actually generate dependencies between the series of p-values. So we can't do that. And so the alternative that we propose is the following one. So we will assume that phi of c has the same kind of project distribution times this copula function that we have here. So if you are familiar with copula function, you already know that this is some device that allows statisticians to take into account dependencies. And if you are not familiar with it, you can just think about it as some kind of correlation function that we add to take into account dependencies. Okay? So here we will have an important assumption, that is that this copula is actually common to all the distribution phi c. Okay? So what do we have to estimate are 2k univariate distribution, which is not too difficult, plus the parameter of one copula function that is not too difficult now. And if we do that, we do account for dependency between GWAS study. Okay, so let's summarize everything. So we have a model about the z-score. This model is actually a model of mixture distribution. These distributions here that appear have a very special shape that is given here. And so for the inference, I will not say that much, except that this inference is done in 2 steps. In the first step, we estimate the marginal distribution F01 and F1k. And this can be done actually separately for each of your traits. And in practice, we do that using a kernel estimation approach. And then you have to estimate all the other parameters, so the proportion WC of the mixture plus the copula parameter theta, and this can be done using basically some kind of classical EM algorithm. So we know how to do that, and once we have done everything, we can compute the posterior probability tau m for each marker m to have a C1 configuration, and from that we can get the p-value. Okay, so enough with technical details, and just let's see how it works exactly in practice. So first we start with simulations. So here we simulate data where we have only 2 traits. So this is a very simple case. 2 traits. We have hundreds of thousands of markers, and we simulated the p-value in a way that it ensures that there is a correlation of 0.3 between these scores. Then what we want to check, what we want to detect actually are markers that are associated with the 2 traits, right? So we tested our procedure and also 10 alternative competitors. And for all the methods that we benchmarked, we ask for FDR control at a nominal level of 5%. So here you have the result. So here each box plot corresponds to a method. And basically what we should get, ideally, would be that all these box plots should be aligned. The box plot displays the FDR, the true FDR level that you get from your procedure. Thank you. And so everyone should be aligned on this red line that corresponds to the nominal level at 5%. As what you can see is that it is not the case. So you have plenty of methods that are available that actually do not efficiently control for false positive. And you also have a few methods that control but very conservatively for the FDR, and the consequence is that they have no power. Okay? So among all these methods, there are basically 1, maybe 2 of these methods that are efficient to both handle the false positive and still have some kind of power, among which the one we propose. Let's now move to a real case application. So here what we want to do is the detection of virus-resistant hotspot, not in tomato but in cucumber. So we had a panel of basically 300 cucumber lines, genotype at 300,000 of markers, and we wanted to investigate the resistance to 6 different viruses. So we run the analysis. The goal was to detect markers that were involved in more than 1 virus, so at least 2 virus resistance. And here are the results that we get. So you can see that we have basically some clear hotspot of resistance. And among the 5 QTL, among the 5 regions that were detected, 2 were already observed in the initial article, but 3 were detected from you. Okay, so I will conclude there. So I hope that I convince you that we have a valid and versatile way to test for composite hypotheses. And if you are interested in the technical details, you can actually look at the article of Anaïg, and you can also try it by yourself by using the R package QCH that we have available on Crane. Thank you.